Hello, this is Elliott Zaresky-Williams, CTO and co-founder of Neurales, and today we'll be talking about the Neural Lambda Machine with meta-learning. So the Neural Lambda Machine is a Turing-complete model that's also end-to-end differentiable, or what I like to call, diff-TC. And this is really inspired from, DeepMind's neural Turing machine and the differential neural computer. And so we talked about this in the last video that we released about a month ago on the Neural Lambda Machine. So we won't go over too much about those models here, but let's just kind of revisit what the Neural Lambda Machine actually did in the last video. So the previous videos, we really saw that the NLM was learning to sort integer arrays that were a fixed size. And so now the NL in recent weeks, the NLM's capabilities were tested on learning the discrete Fourier transform. So there were some mixed results in the general case, but they did very well on the restricted class of functions. Now, a related question we ask ourselves is, what if we could learn multiple tasks simultaneously, right? So although it's hard, going to the Fourier transform example, while it's hard to learn the Fourier transform in just the general case, because it did well on boxcar functions and Gaussians, you can simply, if you could learn algorithm for a large set of restricted sub-examples, then you can essentially learn the algorithm in closer to a general sense. So with that, I mean, let's say, the Fourier transform, you have all different kinds of functions you can, of course, consider, but if you started, learning boxcars, then Gaussians, then other kinds of specialized waveforms, over time, you'll probably cover all of the, waveforms that you'd want to see in the wild. So if you can learn them simultaneously, it's sort of almost as good as learning the algorithm in general, even if the algorithm in general is hard for the neural end machine to actually learn through backpropagation. So let's sort of ask ourselves a few key questions. So could we train the neural lambda machine on both unsupervised problems and supervised ones? What about reinforcement learning? How many tasks can we do at once? And then another follow-up question to that is, can we learn a representation that's actually common to all tasks in a way that transfers over to other related domains? This is like a transfer learning problem. The idea is, if you train on a certain set of algorithms, you then want to say, okay, rather than retraining the NLM on a new set of algorithms that are similar to my original set, well, I want to simply just take the weights from the NLM on the first set and then just sort of transfer over to the second set. And obviously, this is kind of obviously a work in progress, of course, but that's sort of an important question we want to keep in the back of our minds. So in this presentation, we'll talk about how the neural lambda machine was used to classify handwritten MNIST digits and also discrete Fourier transforms of boxcars, and it did it simultaneously. So essentially, it's the neural lambda machine is learning an algorithm that can solve both tasks at the same time. And the next update that we do, we'll see the neural lambda machine be able to do sorting arrays, as well as doing the discrete Fourier transform, MNIST, and also a mountain car, which is a reinforcement learning problem. So you'll essentially have a wide variety of different kind of problems. They're all very different from each other in pretty key ways, and at the same time. But for now, it's just going to be just two tasks. So let's just sort of talk about the data overview. So the DFT was the 2 tensor, which is a matrix of shape batch size by 40, and the 40, of course, is the integer length of each array. In the future, we want it to be where we feed in variable arrays, but that is sort of the work required to do that just hasn't happened quite yet. And then the output's going to be a 2 tensor of shape batch size by 40, which represent the Fourier transform boxcars. Of course, so the first we input boxcars that are sampled at 40 points, and then of course we output the sinc function sample at those same 40 points, which essentially is the Fourier transform. And the loss function used to optimize is a custom NLM loss that was similar but not exact to the one used for the sorting. Now for MNIST, we exactly what you expect it to be. It's a 4 tensor shape, batch size by 1 by 28 by 28. The 1 is because it's a single channel, grayscale, and 28th length and width. And the output's going to, of course, be a 2 tensor shape batch by 10. So essentially, for each item in the batch, we essentially output a probability for each class. And obviously, you want to maximize the probability of predicting the right class. And that's of course, where the cross entropy loss comes in. Pretty standard classification setup. And what about the embedding module? So it turns out that the NLM, in order to actually learn how to do all these tasks, we need an embedding module that learns features common to both these data sets, or in general, all the n data sets you want to feed in at a time. And so they have to be fed into their network that's appropriate for their respective size. Because notice that, of course, not only are the DFT and MNIST not the same shape, they're also not even the same tensor dimension. So that's important. So that data has to be fed in somehow through the embedding module. So there's input networks which take in the data set as is, and then those get fed into the embedding module. And then the embedding module uses a proprietary attention mechanism that was developed for the NLM, which makes use of 1D convolutions with residual connections. And this, of course, this is not the only thing that the attention mechanism has, but this is an important feature. And the reason why it's an important feature is because this is the feature that is largely responsible for the shortcut mechanism. Now, essentially, what that does is the neural lambda machine can learn faster algorithms by rerouting feature maps from earlier layers where the confidence goes above a certain threshold. Now, what exactly does this all mean? So let's say we have a network and it has, let's say, 12 layers. And rather than, of course, for an NLM to learn an algorithm, what that means is you take your input, you transform it to the output. So the algorithm, the running time of the algorithm is equivalent to however long it takes to compute a forward pass through that trained network. Now, of course, you can speed up the process, because if you only needed to go through, let's say, 6 layers rather than all 12, that's where the shortcut mechanism comes in. So it reroutes the feature maps from, let's say, layer 6 all the way to layer 12, after, of course, appropriately shaping. And the intention mechanism does have a way to handle that. So that essentially is how the neural language machine is able to learn faster algorithms as it's training. If the confidence, says, okay, I'm confident enough that I want to reroute this because I'm already learning well. I want to see if I can learn the same thing but faster. Okay, now let's talk about the meta learning component. Now, of course, if you're training on multiple tasks, we really need multiple losses appropriate to each task rather than like a simple global loss. So obviously the loss for MNIST is not going to be the same for algorithmic tasks like DFT or sorting arrays, or even like let's say you want to train for object detection or something unsupervised. The loss will not be identical. So to meta learn efficiently, we want the network to spend more time learning the harder tasks and less time on the easier tasks. Of course, this is not strictly, you don't have to do this way, but if this could speed up training, that's really what one of the things meta learning is interested in. So of course, harder and easier are quantified, but that's obviously, and how they're quantified, of course, is always up for debate. But this is how the meta learning comes into play. And the way this is done is we introduce a meta learning vector of parameters which are responsible for achieving this goal. And this parameter vector is essentially was just a weighted sum of individual loss terms for each branch network. And before we talk about the branch network, let's just kind of take a quick little look at all the our favorite gradient update equations. So in the first equation, we see the theta e. That's the weights of the embedding module. And of course, when we update it, we have learning rate. We have obviously our momentum and weight decay. The momentum and weight decay, of course, are optional. You can always just zero those out to kill off those terms in each equation. But they're there for in case people want to train with those. And we do use momentum in the training. So the gradient updates the embedding module, and then notice that the loss here is going to be a special loss that also takes into account this parameter vector down here, which is this is going to be a parameter vector that includes the weighted sum of loss terms, which get updated as we train. And then these BIs are the branch networks. So of course, the input networks take in the data from DFT and MNIST, they feed it through an embedding module, and there's separate branch networks at the end that then correspond to the given task. So there's a branch for MNIST and a branch for DFT for both input and output. And the embedding module is sort of like, you can say, like a central hub for where all these where they all meet. And so the loss for 2, for example, would be cross entry. Well, so the gradient update, this would be updating, let's say, the MNIST network, and then 3 would be updating the DFT network. And of course, in general, you have n+1 equations. You have n branches, 1 for each task, and of course, you have an embedding module, and you gradient update, each way. So each the same way. And so, and then down here, this also, while we use this to control the weight of each loss term, we technically have also looked into using this to explore how often we even update each branch individually. But we'll talk about that a little bit more later. So let's talk about the parameter group. So how exactly do we optimize all these groups? Because obviously there's lots of groups of parameters, n+1 groups really, because the embedding module, it really includes both the network itself plus the meta learning parameter vector. So does each branch get its own optimizer? Do we consider different learning rates? There are lots of different ways we can explore this. So of course, in this particular demo, the NLM uses one optimizer per branch. So each branch is going to have its own, is updated differently with a different set of rules than the embedding module and the input networks. So we have a optimizer for MNIST and one for discrete Fourier transform network, and then we have another optimizer to update the embedding module, which again includes the central embedding module plus the input networks that take in MNIST and the DFT, along with the meta learner. So 2 different parameter groups for this optimizer, and they will have different learning rates. Okay, then some technical notes, right? So if we go back really quickly to this, notice that if we just included this parameter vector, notice that of course if we backpropagate, if we want to minimize some loss, there's a risk that we artificially set these weights to 0, and we don't want that. And so that's why we don't want to artificially incentivize. Sorry, it's probably a better way to say it this way: to move all the weights to 0 to decrease the loss. So the embedding network is a separate group of parameters, and the loss formulation is set up in a way such that the embedding network's loss cannot be low unless the confidence in the learned task is high. So even if we had some undesirable mathematical behavior the meta losses, which again, of course, the meta losses are a weighted sum of all the losses of the branches. So it's going to be a weighted sum of cross entropy loss for MNIST plus the a weight associated to the loss for the DFT. So we don't want just that. We want that plus a special loss for the embedding network. Right. Okay. And then actually, this is the slide we want to look at. So of course, the loss formulation is a work in progress. It probably does need to be refined. There are probably better ways and maybe some shortcuts that can be used. Maybe there's a better way to formulate the meta learning, but it's all work in progress. However, the current formulation is sufficient for learning these two tasks. So empirically, it does work, although maybe mathematically it's not as elegant as some would like. So let's talk about the experiments here. So experiments that are going to be shown, it's going to be trained on a batch size of 60 for 2 epochs. So the same batch size used for DFT and MNIST. This is not strictly necessary to do, but it's possible this may negatively impact the meta learner's performance because everything's the same batch size, is one less thing to worry about essentially. And so that's why the batch size is set to be 60 for both in this case. So in gradient updates, we update the DFT network every batch, the MNIST network every batch, but the meta learner and embedding module will get updated every 10 batches. And this is sort of a hyperparameter that was introduced into the NLM setup. Of course, it may be in future updates, it may dynamically change how often we update the meta learner and embedding module. But for now, we just wanted to see how it would do if we updated those every 10 batches. Maybe it's not necessary to update the embedding until we've learned something significantly new for the DFT and MNIST networks, because maybe the embedding just simply would not be useful. So that's kind of the idea of delaying the gradient updates for the meta learner and embedding modules. Okay, so here's a nice little GIF, or set of GIFs really, that's showing Neural Lamda Machine. So in the middle, we have the meta learner, and of course the red corresponds to the parameter associated to the MNIST loss term, and the blue corresponds to the parameter for the FFT or DFT. So notice that MNIST in this case is easier to learn so far as the network is being trained. Of course, the activations here in the network are essentially this is sort of part of the embedding module, not the entire embedding module, part of the embedding module. We see that the learn program is very sparse, so actually not much is being activated right now. And notice that the learning rate it's set to very, very small, so probably not everything is very active. And this sort of just talks about what's going on behind the scenes. And in the next video, we'll actually show a picture of what the attention mechanism is doing, because it's easier to see exactly when it gets confident. Does it reroute the activation maps? We'll be able to see a little closer look under the hood than just simply showing a visual representation of a learned program. So this program, this Lambda here, essentially is the deep learning representation of an algorithm that learns both the DFT and MNIST at the same time. That's essentially what this is for. And of course, down here, we have the boxcars on the left, which are the original. We have the predicted Fourier transform, which is in the middle, and the true Fourier transform is over here. So we have boxcars, and then we're trying to learn the corresponding sinc function. And the confidence here, so the green is these values correspond to the running correct prediction. So let's say that it's not simply just, oh, did I get it right now? It's more, have I had a history of getting this prediction right in this array index? And notice that, of course, in the middle, close to 0 is where most of the errors occur, and you can kind of see this in the plot if you look carefully enough. More of the errors occur there, and of course, red is when the error is pretty significant, and blue where it's not as significant. And notice, of course, there are 60 waves per batch, but of course, we're only plotting one at a time just to sort of see. So it's the first wave in each batch is being plotted here. Now, if we turn our attention to MNIST, we have the same thing. We have 60 digits at once. And the MNIST confidence, this is going to be a running F1 score. So of course, if the running F1 score goes above a threshold, we want it to be green, blue, red for below a certain threshold, and overall the network, we want the predicted values to sort of be sparse, because obviously when you first start out, the network thinks, oh, everything is roughly equal probability, but as you train, hopefully pretty quickly, you'll see that the probability mask is concentrated towards only one digit. So you kind of want just kind of one highlight per row. That's what the network wants. We want the network to predict that. And on the right here, we have the optimizer chosen for MNIST. We used an atom optimizer for that branch network. Remember the output branch. The input, the learning rates here, obviously the momentum doesn't count for atom, and no weight decay was used. For the discrete Fourier transform network, we use RMS prop for this one. And empirically, this actually turns out to work for both the sorting and also the discrete Fourier transform. And the learning rate, is 2 times e to the -4. Just learn it slowly. And then this is the momentum used. And for the meta learner and the embedding network, we actually use stochastic gradient descent. So this and with this learning rate and a momentum. Now we turn our attention to this slide. This is a little different. So this is everything here is the same in terms of the neural lambda plots, but let's notice that the learning rate for the embedding network is much higher this time. It's whole order of magnitude higher. And notice that the program here, the activations are not as sparse as they were in the earlier one. And then if we look carefully, you'll notice the meta learner parameter, it's going to start exhibiting an oscillatory behavior very shortly. So let me just give a second for it to actually do that. So you'll see it's starting to go up. So what's happening here is that the neural lambda machine is thinking, okay, maybe MNIST wasn't as easy to learn as I thought, or maybe I'm spending too much time on learning discrete Fourier transform and not enough on MNIST, and in a way that I'm doing that in a way that's detracting from global performance. So so now here, okay, so now MNIST is getting a little easier. It's getting easier. Okay, now I need to spend less time on MNIST and then a little bit less time on DFT. Okay, and now I'm about to cross the threshold where I spend equal time on both, or rather equal importance to both, and now I'm going, MNIST is getting easier again, and this is gonna cycle through. And in the previous skip, we probably just didn't train it for long enough to observe its behavior. This learning rate's faster, so you get to see it. But we notice that the MNIST, the MNIST is the amount of importance you place on it changes with time. And of course, there's more importance on learning the discrete Fourier transform overall, because of course most of the time MNIST is considered to be easier to learn than FFT. And here the activations are of course a little bit less sparse. So there's more going on in the program with the faster learning rate. It seems obviously the interpretations are there's a lot going on, of course. So if you don't, feel free to always rewatch the video and sort of think about it some more. But I want to make sure to give enough information, try to look at the graphs. It looks like we've gone through a whole cycle, but this essentially is what's going on with the neural lambda machine. We're essentially learning two tasks, and I do want to make a comment about the output. So of course, with sorting arrays, what we really wanted to see from the neural lambda machine, we didn't want to see the loss. We wanted to see that it actually could sort the arrays at the end of the day. So here, rather than showing the array Fourier transforms, it's much easier to see a visual to see how well it's being learned. Of course, behind the scene, these are obviously all arrays, but we want to actually see the waves that are being predicted. And for MNIST, we sort of know what to expect for MNIST. We just kind of want to predict a digit, and this is kind of a little bit more boring because MNIST is kind of very basic computer vision task. So this is not as exciting as of course the discrete Fourier transform, but it's certainly interesting to see that we can learn both of them at the same time simultaneously. And this lambda is a representation of a program that learns both of these tasks at the same time. Then you can of course you can track the difficulty that the lambda thinks each task is at this current training iteration. Okay, so now we've seen that was certainly a lot, right? So let's sort of talk about what this all means. Like, what's the significance of these results? So, which may have been a little bit glossed over in the previous video. So the neural lambda machine really is the first differentiable Turing complete model, which has demonstrated learning algorithm to solve two separate tasks simultaneously, where at least one of them is classically algorithmic. And what do I mean by that? Of course, classically algorithmic is this is not mathematically well defined per se, but classically algorithmic tasks would be your standard algorithm that you would see in many computer science applications, like sorting, discrete Fourier transform, graph traversal algorithms, things that typically require human design algorithms to solve. That is something that's been challenging for neural networks to do, with the DeepMind taking a really good crack at it with the differential neural computer and the neural Turing machine. So the models like that are a new class of deep learning models that I think are going to be very important in the 2020s. So this is the first time that we've seen a model, at least I've seen a model, where you learn two separate tasks simultaneously, one of them being classically algorithmic, the other one being just something extra. The point here, we wanted to show that it can learn something tricky like discrete Fourier transform, and in addition learn an additional task on top of that. Now, the network setup, the loss function, the meta learning framework essentially reduces the training to fine-tuning the branch. So what that means is, obviously there are a lot of things that can go wrong when you're trying to learn multiple tasks at once. You're essentially trying to juggle balls you can't even see. Is really the way I like to think about it. So, but the way it's set up, the neural network machine is set up currently, is that it's designed so that the problem of learning multiple tasks at the same time is only as challenging as learning the most difficult branch. So let's say we want to learn on MNIST, let's say CyFAR 10 at the same time. Then we want to, let's say, do a regression problem and a reinforcement learning problem. The reinforcement learning problem might be the hardest one, and that would be the one that is probably it's hardest to train, because each of the other ones are going to be learned more easily. And the reason why that happens is because the optimizer for each of the branch networks is separate. So if we can train something on CyFAR and MNIST, then if we attach it to an embedding module, then that's not gonna detract from the performance. So that's why the setup is such a way that we reduce it to just solving the branch or learning how to solve the branch rather than everything put together at once. Now the embedding module and the meta learner are bonuses, which could potentially be used for transfer learning in the future. Of course, a little bit of typo over here. It's supposed to be transfer learning here, but that's really the idea. We're trying to learn multiple tasks at once. So notice that if we did the neural lambda machine on, say, a cipher on MNIST, that's of course boring. You would use exactly the same setup as we saw here, with the branch networks, and the loss function of the embedding module. But the reason why this was interesting is because of the Fourier transform. Discrete Fourier transform was the hard algorithm to learn here, and because we solved that, it wasn't significant work at all to add in learning MNIST, and that's because of the way the NLM is set up to learn multiple tasks at once. And that's really what it goes down to. It's essentially learning multiple tasks, and you can learn representations common to all tasks that you train it on, and hopefully in the future a transfer learn. And this is the first time that's really been done. So hopefully this could be applied to, this can certainly be applied to many practical cases, that people can come up with. But so if you had, let's say, 20 algorithms you wanted to learn, the neural lambda machine is mathematically capable of doing that. You probably would need a lot of weights and a very large embedding module to learn your representation for that, but it can be done. It can certainly be done. And that's why in the next video we're going to be going back and learning. Let's go back to the earlier slides. We're going to be learning sorting arrays, DFT, MNIST, and mountain cars. So very different problems, all at the same time simultaneously, and that would really just kind of be, I think, a really good, at this point, proof of concept that the neural lambda machine can really do what we intended to do. So I think that probably wraps up everything for this presentation. So I really hope you guys enjoyed it a lot, and stay tuned for more neural lambda machine updates and also app updates as well. And we'll see you guys in the next video.